Okay, so today we're going to talk a little bit about Module 4, Lesson 1, which is on solving systems of linear equations by graphing. This Module 4 is going to be all about solving systems of equations in different ways. This first method it's kind of nice because it's going to use a lot of the strategies that we've already learned for line graphing. But before we get into that, let's talk about what a system of linear equations is. This is a situation where we know that two or more equations are true at the same time. So, we'll use these little curly brackets to indicate that these linear equations are true at the same time. And then we'll just have two linear equations. And these are not the quadratic equations we dealt with in module 3. These are going back to, what we did in earlier modules where we just have x to the first, y to the first at the most. We don't have any variables with degrees bigger than 1. That's what makes these a linear equation. So we'll just have one equation like this and then another one like this. And we know that they're true at the same time. Okay, so a few things we know about each of these linear equations. Well, we call them linear equations because when we graph them, the graphs are going to be straight lines. And so there's really only three things that can happen when we're graphing these systems of linear equations, because the graphs are going to give us two lines. And the first one, that's by far the most common, is if we have our XY grid like this, one of our lines maybe goes like this, and then the other line kind of comes down here like this maybe, and then they're going to intersect in exactly one point. This is the most common situation where we have two separate lines and they cross in one point. We're going to solve this system by finding this point of intersection. This ordered pair right here is going to be the solution to our system. Okay, now we call this a consistent system. Any of our systems of linear equations that have at least one solution, we're going to call them consistent. That's what the word consistent means in math. It means that there's at least one solution to this. And we also describe the system as being independent. Okay, and dependent versus independent refers to the number of lines that we see after we graph it. Like in this case, I graphed two separate lines. And so this is an independent system. So this is kind of the first case that we'll run into, probably the most common case that you'll see, where we have two separate lines. The solution to the system is going to be this point where those two lines cross. But that's not the only thing that can happen. Let's run through all three cases of what we could run into. If we have a XY grid like this, the second case might be one line comes up here like this, and then the other line comes along like this, and our two lines are parallel. That's the second thing that can happen. Okay, and over here, this was consistent because it had this one solution, and that one solution was at that point where our two lines crossed. In this situation, our two lines are never going to cross. So we would say in this that there are no solutions to this thing, to this system. And we would describe this situation as the system being inconsistent. Okay, consistent means there's at least one solution. Inconsistent means there's no solution. Okay, now this is still an independent system because the word independent means that there are two separate lines. We graphed our two separate lines over here. So this was independent. We still have two separate lines here. So this is also independent. Okay, so this is kind of a special case, but it is a case where we'll just have no solutions. And we describe that as being an inconsistent system. Okay, the last situation that we can run into will be where our first line does something like this. And then our second line is actually right on top of the first line. This is actually more common than you would think because, lines can be the same, but can be, can be moved, can be algebraically manipulated to look quite different. So these two lines right on top of each other basically is what we're looking at there. Okay, and every single point on this line is going to be on both lines. So there's an infinite number of solutions to this system. Every single point on these lines is on both lines, so it solves the system. So there's an infinite solution set, we say sometimes. And so this is definitely a consistent system. Remember, the word consistent means that there's at least one solution. This one, there's an infinite number of solutions, so definitely consistent. But this is the word we would really use to describe this one is the word dependent, right? The first two cases that we looked at were independent because we had two separate lines. And here we graphed the lines. They were right on top of each other. They're really one line. So this is a dependent system. In that special case, we're going to have an infinite number of solutions. Okay, so now we're going to look at a specific system and we're going to answer some questions about it. So we've got this x plus y equals 7, 3x plus 5y equals 29. We've got our two linear equations with our curly brackets over here that tells us that this is a system. It means the two lines are true at the same time. We're going to determine whether a couple of points here are solutions to the system or not. Okay, so points that are solutions to the system are going to satisfy both equations. And so this is a good example of why you have to be a little careful with these, because if we take this point 5 and 2, it's got an x and a y in it, and I just plug it in for x and y in these equations, needs to satisfy both for it to be a system. And this one definitely satisfies the first one. If I plug it in for the first equation, 5 plus 2 equals 7. I get 7 equals 7, I get a true statement. So this one does satisfy the first equation, but if I plug it into the second one, 3 times 5 plus 5 times 2 equals 29. I would get 15 plus 10. I get 25 equals 29. It doesn't work there, okay? And so the answer to this one is no, this is not a solution to the system. It works in the first one. It doesn't matter because in order for it to be a solution, it's got to work in both. We have to be able to plug it into both equations and get a true statement after we've evaluated it. Okay, now the second point, on the other hand, if we plug that in, we do our 3 plus 4 equals 7, works there. Okay, and then we try it in the second one, 3 times 3 plus 5 times 4, work it out, we get 9 plus 20, which is 29. And so we're good there too. So this point here satisfies both equations. So 3, 4 is a solution to this system. Okay, so moral of the story here is make sure you check both equations. Don't plug it just in the first one, have it work, and then say, oh yeah, it's a solution. No, it's got to satisfy both equations. And this first one's a good example of a point where we satisfy one equation, don't satisfy the other equation. So the answer has to be no there. Okay. Okay, so next let's look at a system and let's solve it by graphing. In the last one I gave you some potential solutions. We plugged them in to decide whether they were actually solutions or not. But this time I'm just going to give you the system and we are going to find the solution to this system. And we're going to learn several methods for this, but for right now, we're going to focus on using our graph for this thing. And so our first step, if we want to solve a system of linear equations by graphing, is just to get the graphs for each of these lines onto our grid one at a time. So I'm just going to kind of forget about this second line for a second, just focus on the x plus y equals 9, and I'm going to graph it just like I would have done back in module 2. So this one, because the x and y are on the same side, I just like to use a little xy table and work from there. I like to plug the zeros in. So 0 for x and 0 for y, get those intercepts will quickly and easily give me the 2 points I need to graph that line. So if I plug 0 in for x, this goes away. I get that y is equal to 9. So 0, 9 is going to be a point on my graph. And then I plug 0 in for y, this goes away. I get x equals 9. And so 9, 0 is a point on my graph. So that's all I need to graph this line is just those 2 points. So I'm all set. I'm just going to graph them. 1, 2, 3, 4, 5, 6, 7, 8, 9 up here. And then 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right. Now, the nice thing when you're doing these things in MyMathLab is it will make a nice straight line for you. That is extremely important when you're using this method to solve these systems. you have to have nice straight lines. So if I'm going to do this on this piece of paper, I'm going to really need to draw a straight line. So I'm definitely going to need to use a ruler, and I need to have some graph paper, and I need to be pretty precise in order to do this accurately enough to get my solution. So there's my first line. Okay. And so now I'm going to forget about that first line for a moment, and I'm going to do the same thing for the second line. Set up a little XY table, plug in those zeros again so I can get my intercepts. I plug 0 in for X, this goes away. So I just divide by -1 on both sides. I'll get Y is equal to -1 for my Y intercept. Plug 0 in for Y, this one goes away. I get X equals 1. Okay, there's my 2 points that I need. So I'm just gonna go ahead and graph those. So 0, -1 is down here. 1, 0 is over here. And again, I do need to do my best to be as precise as possible. So I'm going to get my ruler. If I'm doing this by hand, really no choice here. Got to make sure I have a nice straight line. Otherwise, I won't be able to find the intersection point that I'm looking for. Okay, so there's our line there. Okay, and so this is going to be kind of that first case we talked about where we have our two separate lines and they cross at one point. This point right here is the solution to our system. We just need to figure out what it is. It looks to me like this is at 1, 2, 3, 4, 5 and 1, 2, 3, 4. You can see why it's so important to be precise here, because if you're just a little bit off with your line, if you're not using a straight edge, if you're just kind of winging it, this point can be off just slightly, and then you're not able to get that point of intersection that we're looking for. Okay, it's maybe a good time to point out a couple of problems with this method when we're solving by graphing. Not every system of linear equations is going to have a point where these things intersect in a nice even value. Sometimes we'll get fraction answers. Sometimes we'll get decimal answers. If we have that case, we try to solve this thing by hand, by graphing, it's just not going to work out. In that case, we would focus more on technology. We would use either maybe a graphing calculator or a computer program like Excel to find those points of intersection. But it is something to keep in mind. You do have to make sure that you're have a nice integer solutions like 5, 4 if you want to use this method and have it work out nicely. So it's not perfect. We have some other methods that'll work better when the answers are a little less nice, but for questions like this, it works out pretty okay. Works fine. Okay, so let's do another one. This time we've got our two lines that are set up for us in slope-intercept form. We know they're in slope-intercept form because they're solved for y over here. Okay, so now the last one we used a little table and we found the intercepts because they were in standard form. This one we're in slope-intercept form. We want to remember all of the little strategies that we used when we were graphing lines before, because when we're in slope-intercept form, there's no reason to set up a table. We want to use the fact that we know that y is equal to mx plus b, and that we know our m is our slope and our b is the y value of our y-intercept, right? So we really have everything we need to know to graph these things right off the bat. So again, I'm going to do these one at a time, just focusing strictly on that first line first. Okay, so for this one, I know my m is 5, which is like 5 over 1, and my b is 4, and that's my y-intercept, right? So if I want to graph this, what I'm going to do is I'm going to start up here at 4. Okay, that's my y-intercept. It'll always be along my y-axis, right? And then my slope is 5 over 1. Remember, slope is like a rise over a run. Okay, so the rise is going to tell me how far to go up or down. In this case, I'm going to go up since my slope is positive. And then I'm going to run 1 to the right. And so again, we do want to take our time if we're doing this by hand and make a line that's as straight as possible. And so my first line is going to look something like this. And if we're in slope-intercept form like this, there's no reason to set up a table. We just want to use the slope and the y-intercept just like we did back in module 2. Okay, so for the second equation here, my slope is 5. And my y-intercept is -2. So I'm going to start down here at -2. Okay, my slope is 5. So from here, I'm going to go up 5. Think of it like a fraction again. So up 5 over 1. And we connect those things up. Okay, and we'll get this line. Now, these two lines, if we're paying attention, we can kind of notice here in our original problem that our two lines have the same slope. Okay, that's what defines parallel lines. These two lines are parallel because they have the same slope, in fact. And if they're parallel like this, they're just never going to cross. This is kind of that special case we were talking about. We would say that this is an inconsistent system because these things are never going to cross. So it's not going to have any solutions. We would also say sometimes that this system has no solution in this case because they never cross. That's what we're looking for when we're solving by graphing. So this is one of our special cases. Our lines are parallel. This one is pretty obvious because the slopes are the same and we're in slope-intercept form. That won't always be the case. It's very easy for us to do some algebraic manipulation to these equations and make it much more hidden than this. So you do want to pay attention to this. Draw when you're doing this by hand, make sure you're drawing it carefully because you won't always, it won't always jump off the page at you as much as this one does. Okay, so let's do one more here. We've got another system of equations that's set up. This is another one where our X and Y are on the same side. So we're in standard form. Again, you want to be flexible. You want to use the slope intercept form when you've got that Y equals on one side, but when you have the X and the Y on the same side like this, I would recommend just using the table and getting your intercepts. It's the quickest and easiest way to graph these things, but the approach doesn't change. We're just going to kind of forget about the second line for a moment. We're just going to look at the first line and we're just going to set up a little XY table. Okay, and then we're going to plug a 0 in for X and a 0 in for Y to get our 2 points. If we plug 0 in for X, this is gone, right? So we get negative 6Y equals 24, divide. We'll get Y equals negative 4. So there's our Y-intercept for that one. And then when we plug 0 in for Y, we get rid of this piece. We get 3X equals 24, divide. We'll get X equals 8. So there's our 2 points that we're looking for. So 0, negative 4 down here, 8, 0 over here. Connect those up and we're good to go. Can be precise if you're doing this by hand, but MyMathLab will be precise for you when you're doing it in there. So that helps. So there's our first line. Okay, so now I'm going to kind of forget about the first one, just focus on the second one. Set up a little XY table for this one now. Okay, and plug in my zeros. So if I plug 0 in for X, this one's gone. Okay, so I get 2Y equals negative 8. Divide. Y equals negative 4. Goes there. Okay, and then I plug 0 in for Y. This piece goes away, right? So I get negative X equals negative 8. Divide by negative 1. We've got our X value. Okay. And so if I plot, you'll notice these two tables ended up being exactly the same, right? So when I go to graph the second one, 0, negative 4 is there, 8, 0 is there. My lines are going to lie right on top of each other. And for this one, for a lot of students, it's not going to jump off the page that these two lines are really the same line. In fact, all I did to get the first line was just multiply this second equation by negative 3 everywhere. Okay, so they're really the same lines, just kind of disguised a little bit there. Okay, so this is our other special case that we're running into here because our lines were right on top of each other. This is definitely a consistent system. In fact, there are an infinite number of solutions here. So sometimes we would say that there's an infinite solution set to this. Okay, but the key word that we would use to describe this system is dependent. There are not two separate lines here. So we would describe the system as a dependent system where the lines are, right on top of each other. Okay, so hopefully that's enough to get you off to a good start in this lesson. Please don't hesitate to let me know if you have any questions at all, and have a nice day.